Now we turn to step 2 of the 5-step analysis. So we're going to do cross-classified DSEM with cycles. And if we remind ourselves about the analysis steps on slide 6, we are now at step 2 here. So we did step 1, finding the cycles by an exploratory analysis, where the cross-classified DSEM used between time estimates for an unrestricted analysis of the cycles, just trying to find out what it looks like, what their duration is. And we also showed how to plot the observed means and the time-specific estimates. In step 2 then, we take a more confirmatory approach. We're deciding on a specific model. We're going to talk about the so-called Cosinor model. We're still in the fixed cycles coefficients setting. That is, we don't allow the cycles coefficients to vary across individuals. Now we're going to take a look at the cross-classified DSEM with cycles and show how to plot the estimated cycles curves using loop plot. So on slide 11, we're focusing then on the cross-classified DSEM with its between time part. And we see that we have these latent variables y on the between time level, which now are predicted by observed variables which are on the between time level. So there are observed variables x1 and x2, which are two predictors of this latent variable. And that regression then has coefficients beta 1 and beta 2 and the residual as well. Now these two predictors are what we need to capture the cycles. They're not just any predictors, they're very specific predictors that enable a sine-cosine shape for the analysis. And our aim is to estimate these coefficients, which later on we're going to allow to vary across individuals. On slide 12 then, we take a look at the basic Cosinor model, the simplest Cosinor model. We're going to take a look at several different versions that are possible in the Mplus program. So the aim is to fit the cycles by regressing y at time point t on two covariates, x1 and x2. And those covariates have known values that are formed by taking the sine of 2 times pi, pi being the usual 3.14, and with a frequency index called omega and the time value t. And I'm going to talk about the frequency index in a second. X2 then uses the cosine function, and you have 2 times pi omega t there as well as the argument. So here you get a chance to practice your trigonometry knowledge, although you don't need to know very much at all. The omega component here is a frequency index, as I said, and in this case it's simply 1 divided by 8, where 8 is the duration of the cycle. And since we have 3-hour bins, 3 times 8 is 24, so the 24-hour cycle is represented by these 8 time points. So again, omega is 1 divided by 8. So we have a simple linear regression here with intercept and slopes beta 1, beta 2 and a residual. But what's interesting about these cycles coefficients, beta 1 and beta 2, is that they carry information about features of the cycles that have more of a substantive interpretation. So beta 1 is amplitude times this sinus component, which then includes a phi coefficient. So that is the phase coefficient. I'm going to say more about that in a second. And beta 2 is a times cosine, the same thing. So we estimate two coefficients, beta 1 and beta 2, but they correspond to two other coefficients amplitude and phase, which have more of a substantive interpretation. Amplitude is defined as half the difference between the highest and lowest y values. So that's a shift in a vertical direction. Phi is a phase shift. So that's a shift in a horizontal direction. And omega is the frequency index I mentioned. And we have these relationships. Amplitude is the square root of the sum of the squared beta coefficients. So when the beta coefficients are high, amplitude is high. Now the phase shift is a little bit more tricky. It's tan inverted of the ratio, which is harder to see through directly, but we're going to talk about it in a more tangible, down-to-earth way on the next slide. And actually, this equation 5 isn't as simple as it's depicted here, and it's often depicted in writing. Section 2 of the supplemental material discusses the details of that phi definition. So on slide 13, we are looking at examples of Cosinor curves, 4 of them, and for the case of omega 1 divided by 8. So we have 8 time points here in day 1, 8 time points in day 2, 8 time points in day 3. So you can think of it as 3 different days. So you look at it in a very broad fashion then. At the top, you can consider this to be a curve for tiredness. You know, tiredness is low in the middle of the day, higher in the morning, higher in the evening, whereas at the bottom, those curves may represent positive affect, but the positive affect is high in the middle of the day, lower in the morning, and lower in the evening. Now, if you look at the top curves then, you have B1 and B2 correspond to beta 1 and beta 2. So here the sine and cosine components have the same weights, same coefficients. So that's the red curve here. And you see then that the red curve has a higher amplitude from low to high. It's higher than for blue. So higher amplitude for red, and that's because the sum of the square root of the sum of the squares of these is higher than for the blue curve, where beta 1 is only half as much as in beta 2. So depending on the weights of the square roots of them, sum of the square root of the sum of the squares, rather, hard to say, you get different amplitude. But you also see that the curves are shifted sideways by emphasizing sine or cosine more. So for instance, the red curve peaks later at night. These are people who are tired after midnight, have their tiredness peak there, whereas the blue curve, they get tired, they have their peak a little bit earlier. So that's the shift in phase sideways that we just illustrated. Now, the difference between the top and the bottom is simply a change of sign. So that simple sign change captures the difference between tiredness and positive affect. On slide 14, I point out that there are different kinds of Cosinor model versions that you can do in Mplus, different levels of generality. So I've listed here the models and how many parameters each model has in the standard univariate case, single outcome, and in parentheses the run numbers referring to the analysis steps of table 1 of the paper. So the 3 main categories are 2-level RDSEM, cross-classified DSEM, and cross-classified RDSEM. So let's talk them through. The 2-level RDSEM can be considered the standard Cosinor model used in the literature. It's been used both in medicine and in psychometrics in many different applications. So you have the cycles modeling on the within level, within person level. And we have two versions of each of these three main categories: the fixed cycles coefficient and the random. For 2-level RDSEM, the fixed cycles coefficient case correspond to that slide 12 that we just looked at. Slide 12 here, this model, where this residual has an autoregressive feature added to it. So this model has 6 parameters. I call it run 2C. Now the random cycles version of that, in that case, has 11 parameters, 5 more parameters coming from the variances of the two random coefficients, 1, 2, and the covariance between them, and their covariance with the random intercept, so 2 more. 5 parameters more, adding to 11. Now, I will focus in my demonstration here on cross-classified analysis of cycles, because step 1, after all, was a cross-classified analysis, and we can stay in that framework a little bit longer. So we're going to look at 2 cases: cross-classified DSEM, where the cycles are on the between time level, and cross-classified RDSEM, where the cycles are on within, just like for 2-level. So the cross-classified RDSEM, cycles on the between time level, in the fixed cycles coefficient case, that is exactly the slide 11 model that we looked at earlier. This model, fixed coefficients, and the cycles modeling takes place on the between time level. So that's there. And that model has 7 parameters, and it's run 2A. So here we see already that this model, fixed cycles coefficients for cross-classified DSEM, has 1 more parameter than the 2-level RDSEM, so slightly more general, due to the addition of a variance component for the between time level. Now the drawback of this is that we cannot work with random cycles coefficients. This model is not available because the cycles are on one of the 2 higher levels, and therefore you cannot make them random. Instead, we go to the cross-classified RDSEM with cycles on within. So whenever the cycles are on within, it becomes a residual DSEM model, just like it is for 2-level. And in this case, we can work with fixed cycles coefficients. It's a 7-parameter run, and we can work with random cycles coefficients, 12-parameter run, adding the 5 parameters like we discussed. So this is a model that we're going to turn to towards the end of the talk. But right now we're going to focus on the cross-classified DSEM, particularly the fixed cycles coefficient case. Note also that the models used in the cross-classified fixed coefficient runs 2A, this one up here, and 3B. They both have 7 parameters. They're actually equivalent, those 2 models. The benefits of the 3B approach, we're going to talk about that when we look for significant deviations from the cycles. So although this is a little bit more of a time-consuming run than this one, it has some benefits in terms of easily finding significant deviations from the cycles. Now on slide 15, we turn to looking at the results of the step 2A analysis, where we have a cross-classified DSEM Cosinor analysis, the fixed case, where we have the plots of cycles in red and between time estimates in blue. So again, the blue are the between time estimates, and the red are the cycles curves. You see the cycles, the red curve here, going up and down in a very regular fashion. And they're trying to fit to the blue curves, the between time estimates. And they do a reasonably good job. We have a fairly high R-square value, 0.41. Now, how did we do that? You have the input here on slide 16. So we have 3 use variables, PA and x1 and x2. We have cross-classified, so we have 2 cluster variables, ID and time. And the t-interval statement is again the same as before. Hours coming from the names list, and 3 hour bins, 3 times 8 being 24, and time is our new time variable. And that is supposed to be the same as the cluster variable that you have there, same name. Now on the between time level that we designate like this, we vary x1 and x2. We let them be between time variables only. They only vary on the between time level. And we have a lag1 model for positive affect. And then in the define command, we create these x variables. So sine and cosine, where 6.28, etc. is 2 times pi. And then 1 divided by 8 is the w, and time is the t that we had in the formulas earlier. Same thing then for cosine. And we use a lot of decimals here to get good precision. And then we do a cross-classified analysis using the base estimator. And you may want to use thinning 10 here to not record as many, skipping every 10th, and maybe also getting more reliable standard errors because you have less autocorrelation in the draws, in the iterations. Slide 17, the model continues. The model refers to the within part, the between ID part, and the between time part. So now on within we still have this auto regression of lag 1. Between ID we'll let PA vary, and we're going to use the intercept, or the mean rather, of PA in a formula later on, so we give a label P0 for it. And then we have the between time part of the model where PA is regressed on x1 and x2. So that refers to this slide here. PA regressed on x1 and x2. We have these coefficients beta 1 and beta 2. And we give those coefficients the names of parameter 1, parameter 2, so that's beta 1 and beta 2. And then we add a model constraint section to do a loop plot. We have a loop of time going from 1 through 56. That is all 7 days. 7 times 8 is 56 with step 0.1. And we plot PA cycles and also what I call factor score cycles. So that's the between time specific estimates that we call B2A at one point. So the PA cycles is the mean plus P1 times the first x, which is this, x1 here, and P2 times the second x, which is the cosine part here. And the FS cycles is the same, but you don't add the P0, so you have that on a different scale, so to say. And you have the usual output standardized Tech 1, Tech 4, Tech 8. And you want to plot this, and you want to have a good amount of factor draws, 200 in this case, to get good estimates. So here is a demonstration of the plotting for the analysis 2A. First I'll talk about how you insert a loop plot in the time series plot. That is how we get the graph on slide 15. And then in that context I will also talk about saving plot data, which is useful for plotting curves from different analyses. outside of Mplus. And just going through that briefly here, in the plot data in the 2A model, column 1 gives x-axis values for the 8 time points per day. So the column 1 values range from 1 to 56 for the 7 days. Column 2 gives the corresponding estimated B2A values, so 56 values. Column 3 then gives x-axis values for a loop plot, which uses a certain chosen step. I used 0.1 here to get a smooth curve. So there will be more x-axis values in column 3 than there are in column 1. Column 4 then gives the cycles values in the loop plot, and they therefore repeat. After 8 days after 8 time points you start over with the same value at time point 9, 17, etc. So we have 4 columns in the 2A setting. In the 1A setting you only have 2 columns, the x-axis values for each time point and the B2A values. You don't have any loop plot there because you don't have any cycles function in post. So turning now to the actual plotting of the cycles functions using the loop plot, let's go to the Mplus output and look at the time series plots again. And we're going to focus on B2A, and we'll look at the mean of it in the posterior distribution. And we're going to add an offset here to get it on the scale of PA as before. So here we have it. And now we can add the timelines again. To keep track of the days. Now we right click and look for Insert Loop Plot, and we put B2A on the scale of the PA variable. So what we want to compare it to is the PA cycles version, which has that extra intercept in it according to the model constraint. So we add that, and lo and behold, here come the cycles. So we see that the if you get rid of that for a second, we see the Tuesday, Wednesday, Thursday, Friday, Saturday. We see a deviation on Saturday where the cycles tend to underestimate the time-specific estimates from the model. But overall, it seems to follow the development quite well. There will be deviations, but it follows it quite well, I think. And this is the same as slide 15. Now, if you want to save data from this, and I'll show you a reason for it shortly why you would want to do that, you would save the plot data and you would give a file name down here and just save it. And the file that gets saved has the column structure that I just discussed on slide 18. Let's for a moment turn back to slide 15 and the step 2A analysis, where we impose a certain cycles function. That is, we do a Cosinor analysis. What we showed here on slide 15 are the cycles in red and the between time estimates in blue. They look like they're fairly close to each other. We have this R² value of 0.41, which isn't too bad. But there's something that's not quite right. And that's the fact that the estimated between time values, the blue ones, are estimated from the model where we impose the cycles function. So they are artificially close to the cycles because of this. What we really would want to do is to compare the cycles, the fitted curves, to between time estimates that are not obtained from the model with the cycles imposed. So that would be the same as looking at the model of slide 8 in the step 1A run. Those are the unrestricted between time estimates, not guided by any specific cycles function. They would be more neutral, so to speak, more closely related to the data, and therefore give a more correct assessment of the fit. The step 1A curve, the blue curve of slide 8, we call those estimates unrestricted between time estimates, not restricted by any particular cycles function. So I just want to repeat that and point out, because we have the option of presenting a more fair assessment of fit. And that's what we show on slide 19. Here we have a Cosinor model, but it's obtained from 2 runs. The cycles are the curves that we looked at before. Now, however, these red cycles are the same, but now they're paired up with a slide 8 between time estimates, the so-called unrestricted estimates, in blue. So now you see a slightly different blue curve than what we had before on slide 15. But I would argue that the discrepancies are occurring in the same spots, for instance, for Thursday here and for Saturday. It's Thursday overestimation, Saturday underestimation. If you compare that to slide 15, going back to that, you have the same phenomenon, overestimating Thursday, underestimating on Saturday. So the picture that we have here on slide 15 is not too misleading, but I just wanted to show you that you can actually produce the curves that give a more fair assessment, but it would have to be from 2 different runs, as I point out here on slide 19. And that's why I wanted to show you on slide 18 how you do the saving of the plot data to produce the values. So you save the plot data from the 2 different plots, and then outside of Mplus you can therefore create a plot like on slide 19.